Alright, let's start with this representation theory problem. So we want to prove that this natural map is a G intertwining map. And you might ask yourself, what is the natural map? And the natural map, let's recall how we define this. So recall that phi is such that for any xi in v star, which is v dual, and for any w in w, so rho acts on v star tensor w, so we take xi tensor w, and this is the map. Oh, that's not a rho, that's a phi. Phi of xi tensor w is the map which sends v to xi evaluated at v times w for any v in v. So remember, v is a vector in v, and xi sends v into c because it's in v dual. And so this part is just a constant, and we're multiplying it by w. And so, of course, this is going to be a map from v into w, and it's going to be linear. You can check that. And so it's in Hom C VW. Okay, so we have that. All right, so let rho v and rho w be representations of G on v and w, respectively. I like to write out these rows explicitly, so that's why I'm doing that. Recall let's see here, then we have representations of G on v dual tensor w and Hom C VW given by, let's just do each of these one at a time. So first we got rho of v dual. Evaluate this at G. Well, that's going to be a representation of v star. And so we gotta, in order to see where this sends it, let's see where it sends an element xi. It's going to send an element xi to another element of v dual. Therefore, to figure out what this is, we have to evaluate this at v. And this is going to be defined to be xi of rho v g inverse evaluated at v. Okay, so this is rho v star. And then we have, let's see here, let's actually move this over to the middle. Nope. Come on. And let's move. There we go. Alright, so that's this. Then if we have rho v dual tensor w of G, well, we're going to apply this at, oh man, I have a typo here in my notes. So this is going to be acting on the tensor product, and so we evaluate it at xi tensor w, and then of course this also needs to be evaluated at v because xi is being evaluated at v. And so what this is going to be is, this is going to be rho v star of G of xi of v tensored with rho w of g w. But then using the previous step, we can actually replace this thing on the left here with xi of rho v g inverse v tensor rho w g w. So this is an uppercase W. I'll try to make it more pointy, and this is a lowercase, so I'll try to make it more squiggly. Okay, so yeah. Okay, so that's that. And then lastly, we have row home of G. So we're going to evaluate this on F, where F is in Hom CVW. And so in order to figure out what this is going to row Hom G is going to map from Hom CVW into Hom CVW. So this whole thing in brackets here is going to be an element of Hom CVW. So in order to figure out what it is, we have to evaluate it at some element V of capital V. And so this is going to be row W of G evaluated at the element F of row V G inverse V. And this is, of course, where G is in G, V is in V, W is in W, Xi is in V dual, and F is in Hom C VW. Okay, cool. So let's see here. We want to prove that phi is intertwining. So we need that that thingy to hold. So anyway, so now for all V in V, W in W, and Xi in V star, if we let F denote the element of Hom C VW given by F of V equals Xi VW, then what happens? Then we basically use a whole bunch of this stuff that we've already proven, and we end up with exactly what we want. So first, what we're trying to figure out is row hom, I guess, G, composed with phi. We want this thing to equal phi composed. What we want is we want this to equal phi composed. So this is equal to question mark phi composed with row V star tensor W. That's what it means for phi to be intertwining. And so, anyways, to figure out what this is, we have to evaluate this at Xi tensor W, and then evaluate that at V. And so let's figure out what this is. So we want this to equal this, evaluate at G, evaluate at Xi tensor W, evaluate at V. Is that tensor? I guess it doesn't really matter if you make this a tensor or if you make this just a comma, because the underlying set is the Cartesian product. It's just that when you have the tensor product, you're imposing different relations on the elements. But anyways, that's all not super important. That's just more like bookkeeping. So anyways, this is how we define phi of this thing. We defined it to be Xi of V times W. So then this is just row hom of G of F of V. We defined F like this so that this would be more transparent, that this is what's going to go from this step to the next one would be more obvious. So then what is this? Well, this by definition is row WG applied to F of row V G inverse V. Okay, well, now what can we do here? This is just row W of G of, and then this stuff on the inside, again, we can write this again as Xi of row V G inverse V W, because that's what F is. So we only introduced F to get from the first step here to the fourth step really easily. So maybe if you can understand what's going on there better, you can skip those steps, but I like seeing all the details. But anyways, okay, so we're here. So now what? Now what we do is, remember xi is an element of V dual. So it will send an element of V to a scalar C. So what we're doing, rho WG takes elements of W to elements of W. So here rho W of G is just being evaluated at this scalar constant times W. And since rho W is a homomorphism, that means that it's, since rho WG, since rho W is a representation, rho WG is a linear map. And so this constant, we can just pull it out front here. So this is just the constant xi of rho V G inverse V times whatever rho WG of W is. Okay? And so now what is this? This is just, by definition, phi of xi, I should write that xi a little more squiggly, xi of rho V of G inverse V tensored with rho W G W, because that is precisely how phi works. Yeah, you just take the thing on the inside and evaluate. You just take this. So if you evaluate phi at this thing, phi whatever, then you're taking this thingy and evaluating it at V, right, and then multiplying on that. So this is the W, and this is the function, and it's being evaluated at V. So if you look up if we go back to what phi looks like, phi is the map which sends V to xi VW. So down here, phi is going to send the element V here to xi VW. So here, this whole thing is playing the role of W, this whole thing is playing the role of xi, and this is playing the role of V. Using that previous notation. These, of course, this xi, W, and V, the ones that I just wrote, are kind of abusive notation because they're not the same thing as the xi's and the w's that you see in this step. But anyways, alright, so we have this. So this is phi of rho V star tensor W of G of xi tensor W V. But this is phi of rho V star tensor W, just rewriting it, of G of xi tensor W of V. I mean, I didn't have to write this last step here, but this makes it really obvious that this is intertwining. So let's see here. This holds for all V, and since it holds for all V, we know that rho hom G this equals this whole thing. And since this holds for all xi and all W, we know that rho hom G composed with phi equals phi composed with rho V star tensor W. And hence, phi is G intertwining, because that's exactly what you need to check. You need to check that this property holds. Well, in addition to it being linear, but we already know that phi is linear because it's a natural. We've already discussed that this phi is a natural map and that it's linear, and so now we know that it's G intertwining, and so yeah, there we go. This completes the proof.